Hello, hello, hello. Am I audible?
Yes.
Okay. So actually, we were discussing about the rotational spectroscopy. Okay. In the last lecture, what we have obtained is the uh, rotational spectra for the diatomic molecule. Okay. So now the what is the intensity? How can we relate this intensity of the spectra? Okay, so let me just describe this. So the intensities of the spectral lines. So if you see the last spectra, so you can see here we have these different transition. The selection rule is delta J is equal to plus minus 1. Okay, where J is the rotational quantum number. Okay, and we have different lines there, 2b 4b at 2b 4b 6b 8b 10b, different lines. And the what are the intensity of these different lines? So these the expression for that has to be find out. So the intensities of the spectral line, intensities of spectral lines, uh, intensities of spectral lines. Okay, so uh, actually, in order to find out the relative intensities of spectral lines, so you should have the knowledge of the relative probabilities of the transition between the various energy levels. Okay, so actually this intensity of the spectral lines, it will be directly proportional to the initial number of molecules in each levels. Okay, so if you see, if you assume that the initially we have n naught molecule, n naught molecule initial level. Okay, and suppose nj is the molecule at jth level, molecules at jth level. Okay, so uh, the relative intensity expression for relative intensities can be written like this. So we have nj upon n naught. N naught are the molecules in the initial levels, nj at any level having quantum number j. So this is actually given by the expression exponential of minus of ej upon kt, minus of ej upon kt, and which can be further written like this, which is equal to, if you write in terms of the constant, this rotational constant b, so it will be exponential of minus b hc j into j plus 1 upon kt. This is question number 1. So here you know that the ej upon hc. Okay, we have already find out this expression. This epsilon j is nothing but this is equal to ej upon hc. This is equal to b j into j plus 1. Okay, so this is the expression for the intensities of the spectral line. Okay, so let me just find out this the for a particular value. For example, we have given, if we have given the b in centimeter inverse, b is actually in centimeter inverse. Okay, see if you can do a simple calculation, and we can see here that is nj, actually nj number of molecules at jth level or upper level, or you can say the population inversion. Sorry, population of the, not population inversion, population of the upper level. Okay, this nj is basically, it is depending upon the j. It will vary with the value quantum number, rotational angular momentum quantum number. Okay, so if you have given, for example, we have given b, which may be like 2 centimeter inverse. Okay, and T is temperature, T is the room temperature, for example, that is the 300 Kelvin. Okay, and we can find out the relative population in J, in the J equal to 1 state. So relative population in J equal to 1 state is, it will be given like this. So it will be relative population n1 upon n naught. This will be equal to exponential of b is given to you, which is the 2 centimeter inverse. So you can just write like this: so 2 multiplied by 6.63 into 10 to power minus 34, value of h, multiplied by 3 into 10 raised to power 10. Okay, c value of c, and then multiply by 1, multiply by 2, j into j plus 1 upon kt. K is the Boltzmann constant, which is equal to 1.38 into 10 raised to power minus 23 into 300. So its value is actually equal to, nearly equal to exponential of minus 0.019, which is nearly equal to 0.98. It means that, what is the meaning of that? Almost same number of molecules, you can say. There are almost as many molecules in J equal state at equilibrium. So it's the same number of molecules can be obtained in the upper level with J equal to 1. Okay, so in other words, J equal to 1 levels have almost same number of molecules as in the J equal to 0 state, or in the, you can say, in the ground state. But it will decrease rapidly with the value of J. Okay, because this n naught, n upon, you can say nj upon n naught, it is proportional to J. Okay, it is proportional basically J into J plus 1, and B is also there. Okay, so if you draw a curve for different value of B, okay, so the variation of J with the this population, it can be drawn like this. If you draw a curve for the relative population versus J, so this is J value in the x-axis, and in the y-axis we will have the exponential of, or e raised to power minus bj into j plus 1 minus bj into j, means bj plus 1 hc upon kt. Okay, hc upon kt. Okay, so this relative population is maximum here at 1. Okay, and it will be varying like this. So we have and this is 1, this is 0.5. Okay, 0.5 here, and 0.5 here. Okay, so if you have given that value of B, this is, for example, 5 centimeter inverse, and 5 centimeter inverse. So for B 5 centimeter inverse, it will start from this maximum value. Okay, the relative population is maximum here at J equal to 0 is here. This is 0 to maybe 1, 2, 3, 4, 5, 6, so on. Okay, so it will go like this. Okay, this is for B equal to 5 centimeter, and so another curve will be for the bigger value. For larger value, so it can be like this. Okay, so this is for the B equal to 10 centimeter inverse. So in this way, with the increasing value of J, relative population, it will go on decreasing. Okay, relative population at the higher levels in these rotational energy levels, it will go on decreasing. Okay, so this is the curves for the relative population versus the rotational quantum number J. But this relative population is not only depending upon J, it will also depends upon the its degeneracy. Actually, this J it doesn't have a single energy levels. For a given value of J, there are two J plus one values. Okay, for given J, actually, but for given J, there are degenerate levels similar to that of the angular momentum, orbital angular momentum. For a given value of a L, there are 2L plus 1 different values. Okay, for example, if I take the example of the J equal to 1. Okay, so if we have the J equal to 1 molecule, then there are quantum of J equal to 1. So possible the degeneracy of that level, it will be minus 1, 0, plus 1. Similarly, for J equal to 2, it will be like minus 2, minus 1, 0, 1, 2, 1, 2, 3, 4, 5. Similarly, J equal to 3. Okay, so if you draw a curve like this, so we have this uh, this is the reference direction. Okay, and if you see that the this different direction of that J angular momentum, it will be like this. So this is 0. One is this. So actually, this will be like this. So this is corresponding to J equal to 0, and this will correspond to 1. This is 0. This is plus 1, and this is minus 1. So basically what is there, so there is a different orientation. It means that there is a different orientation of the molecule. For example, if one molecule, diatomic molecule, it is rotating, it is rotating here. Okay, this is one molecule is like this is a diatomic molecule. Okay, it is rotating in this direction. One another orientation of that diatomic molecule, it will be like this direction, and another direction of rotation will be like this. Okay, so this is the rotation of the three different rotation of the molecule. Okay, so that particular J value, there will be 2J plus 1, you can say, different orientation of that particular molecules. Okay, similarly for J equal to 2 and J equal to 3. Similarly, if you draw this different direction for J equal to 2, so it will be like this, or J equal to 2. This is for J equal to 1, it will be this 0 for it. This is 0. It will be plus 2, plus 1, and it will be minus 1 and minus 2. Similarly, j equal to 3, it can be like this. This is 0, and it can be plus 3, plus 2, plus 1, minus 1, minus 2, minus 3. Okay, so 2j plus 1, 1, 2, 3, 4, 5, 6, 7 different orientation of the rotation of that particular molecule. Okay, and so on. Okay, so it means that this relative population of the this transition of these molecules, it is not simple. This expression exponential bhcj into j plus 1 upon kt, but there must be some another factor which is 2j plus 1. Okay, there must be some another factor which is 2j plus 1, that is the which will give the degeneracy of these different uh, rotational quantum numbers. Okay, so that value, it is actually the population. So relative population, basically it will be proportional to 2j plus 1, that is degeneracy, as well as the exponential factor, which is nothing but this ej upon kt. So you can write this ej in terms of bhc or the j into j plus 1, or you can just write 2j plus 1, that was exponential of, that was, what was the ej values, b hc bhc j into j plus 1 upon kt. Okay, so this is actually the actual expression for the relative populations of the molecules in the, you can say, the upper level. Okay, so any questions, any doubt?
Excuse me, sir.
Yes, please.
सर इन प्रीवियस आपने बताया था एन जे अपॉन एन नॉट का, वहाँ पे भी एक्सपोनेंशियल वेरिएशन के साथ होगा या सिर्फ बी जे इंटू जे प्लस 1 ही होगा?
कहाँ पर?
सर आपने एन जे अपॉन एन नॉट का आपने जो प्रोपोर्शनलिटी साइन लिया है,
दिस वन 2j plus 1.
नो प्रीवियस पेज में सर आपने एन जे अपॉन एन नॉट का जो लिया है,
कहाँ पर? ये इक्वेशन नंबर 1.
सर एन जे अपॉन एन नॉट प्रोपोर्शनल टू बी जे इंटू जे प्लस 1 आपने जो लिया है, वो एक्सपोनेंशियली होगा वेरिएशन में या सिर्फ बी जे इंटू जे प्लस 1 होगा?
No, this is exponentially actually. So I was just writing that nj upon n naught, it depends upon j actually. So this will be exponential actually. So this is proportional to actually exponential. Actual expression is exponential of bj into j plus 1. Okay, it will be exponential, but I have just in a simple you can say convenient manner, I have written that this nj is proportional to b, or in, you can say that nj upon n naught is proportional to b, and j upon n naught is proportional to j into j plus 1. Actually, it will be exponential.
ओके
Okay,
सर,
I
थैंक
have
यू सर.
written just a simple language that it will depend upon directly on the b and j into j plus 1. This is for the in the context of this graph actually. So we have here j in x-axis. Okay, so this is you can say 1, 2, 3, 4, 5, 6, so on. Okay, j in the x-axis, and that exponential bj and j plus 1 hc upon kt in the y-axis. Okay, any other doubt?
Sir, what's the meaning of population? Population.
When you join the class?
So right now, sir, 2 minutes before.
So why you are late?
My network is not working.
Hmm?
That's why I connecting other. Sir, my net is, sir.
Hmm. So
I
what is
connect another.
population? Population is the number of molecules which are present in the upper level. We are basically discussing about the relative population molecules in the rotational spectra. So these population will define actually spectral intensity. More number of molecules are in the upper level means the intensity of that particular spectral line will be high. Okay, population means the how many molecules are present in the upper level. Means you can say how many molecules are transit from the lower level to the upper level for the absorption spectrum. For the emission spectrum, that population will be reverse. That is, how many of molecules will be are you can say transmit from the upper level to that of the lower level. So in that case, population will be considered for the lower level. Okay, number of molecules present in the relative level, you can say. Okay.
Okay.
So if you draw this curve, so now this 2j, okay, before that, let me firstly actually find out this maximum population. Okay, so a curve is not going to be now the decreasing one, as we see in the previous graph, that with the value of j means increasing the value of j, the population is decreasing. In other way, you can say the intensity of the spectral line is decreasing. But when you consider this factor 2j plus 1 degeneracy, it will be firstly increasing to the maximum, then it will decrease. Okay, so what is going to be that maximum value? Let me just find out this. So let us find out differentiation of that. So this is equation number 2, for example. Okay, so this is equation number 2. Differentiate question number 2 with respect to j. Differentiate question 2 with respect to j to find out maximum value of j. So maximum value of population. That is, let me just find out this dj or ddj of the, you can say, the population, which is equal to, which has to be equated to 0. Okay, this is when you find out this derivative of this right hand side. So it will be, so first you can use here product rule. So it will be 2 e raised to power minus ej upon kt plus 2j plus 1 e raised to power minus ej upon kt minus 1 upon kt dej upon dj. Okay, and further it will be equal to, further if it will be equal to 2 e raised to power minus ej upon kt minus 2j plus 1 upon kt e raised to power minus ej upon kt into ddj of bhc j into j plus 1. I am doing nothing, but I am just solving this derivative, partial derivative, and equate that partial derivative equal to 0 to find out the maximum value of the population. And you know that is a procedure to maximize the any parameter. Here that parameter is the population. This is equal to 2e raised to power minus ej upon kt minus 2j plus 1 square upon kt e raised to power minus ej upon kt into bhc, which is equal to 2 minus 2j plus 1 square upon kt bhc equal to 0.
Hello, sir.
Yes, please. Yes. Hello. Hello, am I audible? Hello.
Yes, sir.
Is there any question, any doubt? Okay. So actually, I am doing nothing but just finding out the derivative. Okay, with respect to j. Okay, so this will be which implies that. Let me do it in the next slide. So which implies that this 2j plus 1 square upon kt bhc is equal to 2, which implies 2j plus 1 is equal to under root of 2 kt upon bhc. Okay, from here you can find that this j, value of j, will be equal to under root of kt upon 2 bhc minus 1 by 2. So we are able to find out the value of j where the population is going to be maximum. Okay, at that value of j, when j is equal to kt upon 2 bhc minus 1 by 2, okay, then the value of that population, the population will be maximum. Okay, so if you just draw this curve for this population versus j, so if you draw this curve of in the x-axis we have rotational quantum number j, in the y-axis we have the 2j plus 1, 2j plus 1 multiplied by exponential minus b j into j plus 1 hc upon kt. Okay, so that curve is actually going to like this. So it will be going from minimum to maximum. Like this, at maximum, it will goes like this. Similarly, like this. So for example, this is the curve for b equal to 5 centimeter inverse. So see, when you increase this value of b, this curve will be, this population will be lower one, because here you can see in that expression that b is in the denominator. So larger the value of b, lower will be the value of that highest value of the population. This is for b equal to 10 centimeter inverse. Okay, so in this way, firstly that curve will go on increasing. Then after reaching the maximum value of j, then it will be decreasing. So this is the actual curve for the relative population of the the rotational energies, you can say, in the transition of the molecules in the rotational energy spectrum. Okay. So that was the rotational spectroscopy and the relative populations of these intensity of the spectral lines. So basically, higher the population means higher will be the intensity of the spectral line. Any question? Any doubt? Any questions? Any doubt? No? I hope I'm audible.
Yes, sir.
Yes, sir.
Okay. So this was the rotational spectroscopy or rotational spectra and related topics. Now, next thing is the vibrational spectra, vibrational spectroscopy. So what was there in the rotational spectroscopy? Rotational spectroscopy is dealing with the rotation of the molecules. Okay. In the vibration spectroscopy, it is related with the vibration of the molecules. Vibrational spectroscopy. So basically, this is actually IR spectroscopy, infrared spectroscopy. So here, the vibration of the molecules will be there. Okay, so it deals with the vibrations of molecules. Okay, now not only these molecules are rotating, but also they are also vibrating. They can vibrate like in harmonic oscillator. Okay, that vibrations are there in these vibration will be there in these molecules. That spectroscopy lies in the range of actually 700 nanometer to up to 1 millimeter. This is the range of the spectroscopy. Okay, so let me firstly describe the simple harmonic oscillator example. Simple harmonic oscillator. So actually, that molecule is not a simple harmonic oscillator. There will be some inharmonicity as well. So firstly, let me describe this simple harmonic oscillator. Then I will be discussing about the inharmonicity in that particular things. This is a simple harmonic oscillator. Okay, so we can ideally assume that these molecules are vibrating like a simple harmonic oscillator. Okay, and the frequency of oscillation of the simple harmonic oscillator, it will be frequency of oscillation can be written like this. It will be omega oscillation bar. This is actually given by 1 upon 2 pi c under root of k upon mu centimeter inverse, where mu is the reduced mass. Okay, mu is the reduced mass of the molecule. Okay, and k is the force constant. Okay, so vibration energies are given like this. So you know that this for the case of the simple harmonic oscillator, vibration energy like this. E V is the V for vibration. This is nothing but this will be equal to V plus half H cross omega oscillation. Omega oscillation. Okay, this is in the joule. Okay, and you can just write EV in terms of the centimeter inverse, which is equal to capital EV upon HC, which is equal to V plus half mega oscillation bar in centimeter inverse. Okay, where V is equal to 0, 1, 2, and 3, so on. Okay, so when V equal to 0, when V equal to 0, you can see V equal to 0, E naught, that is the energy corresponding to the V equal to 0, it will be equal to half omega oscillation. So that it means that these molecules, for example, diatomic molecules, its energy will never be zero. Its vibration energy will never be zero. Okay, so there must be some kind of 0 point energy. So this is called 0 point energy actually. 0 point vibration energy. Its energy, and so the energy of the vibration of that diatomic molecule, it is never be zero. Okay, so there will be some kind of 0 point vibration energy already present in the case of the molecule. So they are already at V equal to 0. They will be vibrating. Okay, and you can just draw the curve for the energy versus distance like this. So the energy versus distance can be drawn like this. So we have this energy in the centimeter inverse. Okay, so energy in centimeter inverse in the y-axis. In the x-axis, we have the R equilibrium, means equilibrium distance. The equilibrium distance is that distance in along which this molecule is vibrating. Okay, so this is internuclear distance. So you can say internuclear. Okay, so curve will be like this. Curve for this kind of spectrum will be harmonic oscillator. You know that it will be like this. Okay, so at V equal to 0, this is the energy, which is the half omega oscillation, that is 0 point energy. This will be half omega oscillations. And these energy levels are equally spaced. Higher energy levels, these are equally spaced like this. Okay, V equal to 0, V equal to 1, V equal to 2, V equal to 3, okay, and so on. So this is half omega oscillation, that will be 3 by 2 omega oscillation, similarly so on. Okay, so in this way, and these spectrum actually, this is equally spaced. If the spectrum is equally spaced, then this energy, this vibration energy spectrum, you can see this equally spaced. If you draw this spectral intensity or spectral line, you will see that there will be a single line. A single line, this is the omega oscillation, because they are equally spaced. Energy spectrum is equally spaced. Okay, so this spectral line will be like a single spectral line. This is in centimeter inverse. Okay, and here the section rule will be delta V is equal to plus minus 1. These are section rules. Okay, so for this case there will be a single spectral line. Now we should here mention that the if there is so the vibration energy change actually, it will it will only give the spectrum, the spectral line, when these vibrations, this vibration spectrum, or these if these vibrations are interacting with the external light. Okay, so what is happening? So see how the spectrum is actually obtained. You just shine a light from the outside to that molecules. Okay, if these molecules are vibrating, then this vibrational energy or this vibrating molecule, they will interact with the external light which is shining on that molecule, so that it will give this spectrum. For this, again, similar to that of the rotational spectrum, here the molecules should have the permanent dipole moment. Okay, if the molecule don't have the dipole moment in the ground state, you can say, then this type of spectrum, the spectral line will not be observed. Okay, so permanent dipole moment should be there for the molecule in the molecules, diatomic molecule, so that the incident light will be interacting with this dipole moment of that molecule, so that the spectrum will be observed. Okay, so let me just write a statement here for the simplicity. Mm. Vibration energy changes. So vibrational energy changes will be observed only when there is interaction between incident light and the dipole moment of the molecules. Okay, so there must be some kind of dipole moment in that particular molecule. So it cannot be like H2 kind of molecule. H2 molecule is like we have the two atoms of that molecule which are same. There must be some asymmetry. Okay, so that there will be dipole moment in that particular molecule. Okay, so actually this is the ideal situation. This harmonic oscillator case is the ideal situation. But in a realistic molecule, they are not vibrating like like this harmonic oscillator. Okay, there will be some kind of inharmonicity in that vibration of the molecules. So how can we? Let me discuss this. Any questions? Any doubt? Any questions up to here? No?
No, sir.
Okay, so let me consider the case of the enharmonic oscillator. So real molecule actually do not oscillator. Let me just write it here. Real molecules do not obey simple harmonic oscillator motion. Okay, so that we have to consider an harmonic oscillator. So an harmonic oscillator is something like that. So what is basically happening? So the molecule can vibrate. Okay, so at some point of time, that bond of that molecule get break. Okay, so the breaking of the molecular bond can happen. Okay, so in that case, the synergy spectrum will be like this. So in harmonic oscillator, so in harmonic oscillator, and in the y-axis we have energy. So actually this curve is like this. At some point of time it will be like this. Okay, so this distance is actually, this is called D equilibrium. This is D equilibrium, that is the that equilibrium distance at which that bond can be broken by by during this vibration. Okay, and actually this type of curve is it is nothing but this is given by Morse curve. You must have uh, they learn this Morse curve in the solid state physics in BSc, I think. A Morse curve, which is given by the expression E equal to Morse expression E equal to D equilibrium, and here it is 1 minus e raised to power some constant a, okay, and r equilibrium distance minus r and whole square. This is Morse equation actually. You must have learned this equation somewhere in the BSc, I think, in the atomic and molecular physics or somewhere in solid state physics. Okay, so this A is the constant, D equilibrium is the dissociation energy basically. This D equilibrium is the, so A is actually constant and D equilibrium is the dissociation energy. That is the energy of the dissociation of the molecule into respective atoms. Okay, so this is the Morse curve and Morse expression, which will describe this kind of actually the form of the curve. Okay, now when you use this, actually this equation number 1 is Schrodinger equation, so you will obtain this energy. Okay, so when you use this equation number, this equation number 1 instead of the equation number that E equal to half h cross omega. Okay, instead of, if you use this expression there, you will see that the energy in that case will be given by, I'm not going to solve it, it is going to be assignment for you. So vibration energy will be equal to V plus half omega E minus V plus half square omega E bar XE centimeter inverse, where this V is equal to 0, 1, 2, 3. Okay, so this is assignment number 1. Find out the vibrational energy for an harmonic oscillator. Using Morse expression. This is assignment for you. Okay, assignment, you have to submit this assignment. So you know that there is some component of assignment in the in this course. Okay, so that assignment you have to solve, and you have to solve actually this. You have to find out this energy in equation number 2. Okay, so here omega is the oscillation frequency and xe is called the enharmonicity constant. We call it is xe here. So here this, so here omega E This is the oscillation frequency. And the XE is enharmonicity constant. Enharmonicity constant, which is very, very small actually. Which is very, very small actually. Its value is actually of the order of 0.01. This value is of the order of plus 0.01. This is very, very small value. Okay, it's very, very small value. So using this expression, you will see that now this energy spacing between the two energy levels, two vibration energy levels are not same. It will be different. If you see this equation number 2, we have V plus half omega E bar minus V plus half square omega E bar XE. So we have some values there. Okay, when you increase this V, this energy spacing is not going to be the equally spaced. It will be it will decrease. Energy spacing will decrease when you increase the value of V. So let me just draw here this curve. So we have like this. This is the, it can be, this curve is like this. This is energy in x-axis, and R equilibriums are in the R in the x-axis and is energy in y-axis. Okay, so you will see that this energy is, this is V for V is equal to 0. So initially the spacing will be like this. So when you go on increasing the value of V, you will see that energy spacing will go on decreasing. Energy spacing will go on decreasing like this. V equal to 0, V equal to 1, 2, 3, and so on. Okay, and if you draw the spectrum, so here the section will be delta V is equal to plus minus 1, plus minus 2, plus minus 3, and so on. So if you draw this, what is the meaning of that? Plus minus 1, plus minus 2, plus minus 3. So there can be transition from this level to this level, first level, transition from this level, also from this to this level. Okay, so if you draw this spectral line intensity, so it will be like 3 levels can be. Okay, so this corresponds to omega E. This will correspond to omega E. Second one correspond to 2 omega E. Third one corresponding to the 3 omega E. Okay, this is in centimeter inverse. This is in centimeter inverse. Okay, so these 3 different spectral line, actually the first 3 are the more significant. Okay, although there are the other energy levels, means if the transition can be from 0 to 4th level, 0 to 5th level, that is plus minus 4, plus minus 5 can be there, but the relative intensity of these lines will be very, very weak. So we can just neglect these different higher transitions. Okay, so we can only have 3 different transition can be taken for consideration, and this first transition is actually called the fundamental transition. Second is called the second overtone. Third is the third overtone actually. Okay, let me first write this energy, that energy expression, that equation number 2. Energy expression of equation number 2 can be written like this. So equation number 2 can be written like this. So this is energy of this enharmonic oscillator, which is equal to omega E. Okay, I have taken some common values there. Here 1 minus XE is the enharmonicity constant. This is V plus half. Okay, and V plus half is taken outside as common thing. or omega oscillation is nothing but omega oscillation will be equal to omega E 1 minus XE V plus half. Okay, and the if you find out these energies, okay, we find out this V equal to 0 to V equal to 1. So it will be delta E. Delta E is equal to, for have delta V plus minus 1 or plus 1, for example, delta V equal to plus 1. So delta E in that case will be equal to E at V equal to 1 minus E at V equal to 0. When you put V equal to 1 and V equal to 0 in that expression here, you will see that it will be equal to, actually, this will be equal to omega E 1 minus 2xe centimeter inverse. Similarly, if you take delta V plus 2, okay, so the delta E is actually going to be equal to, I'm just writing directly, 2 omega. You can check it by putting the value V equal to 1, V equal to 0 in this expression. Okay, delta E change in the energy is going to be equal to 2 omega E 1 minus 3xe centimeter inverse. Okay, similarly for delta V plus 3, delta V equal to plus 3. Okay, change in the this vibrational quantum number is plus 3. Then this change in the energy levels, it will be equal to this will be equal to 3 omega E okay, this will equal to 3 omega E 1 minus 4xe 1 minus 4xe centimeter inverse. So that's, you can see that this energy, it is energy difference basically. It is depending upon, this is proportional to omega E, 2 omega E, 3 omega E. That's why I have written here omega E, 2 omega E, 3 omega E. Okay, so this this first one, it is called fundamental absorption. This is for absorption. So let me just write here delta V plus 1. This is called fundamental absorption. Okay, delta V equal to plus 2 plus 3. These are called first and second overtone. Okay, at higher level also there are third overtone, fourth overtone, but their intensity is very, very weak. So you can just safely neglect these transitions. So only 3 transitions are possible, means it can be considered, that is corresponding to delta V plus 1 or minus 1, minus 1 for the emission, plus 1 for the absorption actually. Okay, so 1, 2 and 3. The first 3 transitions can be taken into account, because these are the only transitions which can be actually observed in the spectrum, and other transitions actually will be very, very weak and they can be safely neglected. So this was the enharmonic oscillator and the related transition, vibration transition actually. Okay, any questions, any doubt? Any doubt? I hope I am audible.
Yes, sir.
Yes, sir.
So any questions regarding this?
No, sir.
No questions? Okay, so you have to submit this assignment. Okay, so you can
Sir,
take
by email, sir, by email or by
No,
written
I-
copies in your office?
No, I will share a link. Okay, Google form link. So you can just upload the assignment on that Google form link. Okay.
sir.
So I am giving you 15 days. Okay, so within 15 days you have to submit this assignment after the exam. Okay.
Okay, sir.
Okay, so if there is no question, then you can leave the class. Okay.